is recording. Okay, it's starting to record. So for the time being, I know an op-amp is not really clear in what it is for. I think the most important part of this course is to perform analysis with it. But of course, you have to know what the practical purpose is, right? Which I think will be touched upon in tutorial 11. So never mind if it seems like a black box to you for now. Okay, so let us just dive in. So question 9.1, the circuit in this figure will remove the DC portion of the input voltage. Okay, so there's an input voltage here in the positive terminal. I know they call it like inverting or non-inverting terminal, but just for common sense wise, I would call this the positive terminal. I would call this the negative terminal of the op-amp. It is indicated by this triangle. This is the op-amp. So they supply some voltage over here while amplifying the AC portion. So we're given this, V1 is modeled using this sinusoidal function. And then they give us the resistance and the battery voltage. Okay, so find the resistance of RS such that there is no DC voltage that appears in the output. Okay, so to cut to the chase, right? All the nitty-gritty from op-amp, what you have to know at the end of the day, right, is literally 3 things that I'm about to tell you. Yes, so take these 3 things with you to the grave, and everything should actually, like, literally 90% of what you should know about op-amp will be done. Okay, so whenever you see the op-amp, immediately write this down. V plus equals to V minus. Then I plus equals to I minus equals to 0. Then the steps that you're supposed to take from here is to do KCL wherever possible. Okay, so you will be doing KCL at wherever nodes you see makes sense to do a KCL. So you understand what it means when we go through the questions. So I'm gonna repeat again. Every time you see this little triangle, which is the op-amp, immediately in your brain, you should click and write this down in your paper. V plus equals to V minus, I plus equals to I minus, KCL wherever possible. Okay, actually, you don't need to write KCL wherever possible, but this is one of the steps, is to do KCL wherever possible. So what does that mean? As far as this course is concerned, the voltage at the positive terminal, the voltage at the positive terminal, which is over here, so this whole node voltage, will be equal to the negative terminal of the op-amp. Always, okay? This is always the case for op-amps, for ideal op-amps in our course. So V plus equals to V minus. This is a fact of ideal op-amps. And another fact is I plus equals to I minus equals to 0, okay? This one must always come with I plus equals to I minus equals to 0, okay? Here there's always a 0, always. But here it's not necessarily 0, okay? So with that in mind, let us start. So we can, with these 3 facts, we can start to do the KCL wherever possible. So emphasis again, please take these 3 steps with you to the grave. Okay. So we know for a fact that V plus is equal to V minus, correct? So let us look at the diagram first. So I just copied down this from up here. It's just an enlarged photo of the figure that they provided. Now, just take a look at the terminals. So the easier terminal to analyze would be this one, right? Because there's not much things connected to it. The only thing that's connected to it is this V1 source. So we know that V plus, this voltage, is equal to V1, correct? Because this entire thing is a node, right? Ask yourself, is there any device inside here? No. So it's one node voltage. I see something in the chat. Hold on. Okay. Sam here to smile. Yeah. So this whole thing is one node, so it shares one voltage value, and that is V1, right? So we know for a fact that from this diagram, V plus is equals to V1. And we know that for ideal op amps, this is always the case. This always holds true. V plus is equal to V minus. So we know that this is also V minus. Okay? So now to decide this, KCL wherever possible. Just look at the nodes that are available to you. So one node will be here. Another node will be here, right? This looks obvious. They already marked it out. This is a node. It doesn't make sense to do KCL here, right? There's not much you can analyze. There's no current going in equals to current going out, any funny business related to this. So it's not meaningful to do KCL here, okay? It is meaningful to do KCL in here, correct? Okay, so how do we do KCL for there? They did not assign us any direction of the current, correct? So what do? We just assume ourselves. Where to assume, right? In this case, I remember back in the node voltage analysis, I always tell you, assume that it moves out. Yeah, true. You can still continue to assume that it moves out. But in this case, it really just is anyhow, really. So you focus on this node. You can really assume that it goes in this direction and this direction. Or you can also assume it goes to this direction and this direction. Or you could also assume it goes to this direction or this direction. I'm telling you, it really is just any way. Just as long as you keep consistent with following KCL, current going in is equal to current going out, any way you assume should be no problem. So for the sake of simplicity, let's just assume this way. Move in like this and move like that. Let's make it simpler. Like this, like that. Okay? And then what about this second law that I put down here? I plus equal to I minus equals 0. That means the current going into the positive terminal, is equal to 0. So there's actually no current flowing through here. Yeah, in this strand of wire, hold on, let me highlight it. In this strand of wire, there's no current actually flowing into the op amp. Same for the negative terminal. See, I minus equals 0. So the current flowing into the negative terminal of the op amp is 0. So only this portion, this segment, hold on, I'm going to circle it. Only this one, immediately before the op amp. This one, 0 current. Okay, 0 current flowing into that. Now with that in mind, we can start to do our KCL. So let us focus on this node that I circled. So KCL means current going in equals to the current going out. So who is the one going in? This one, correct? This is the current that is moving into it. And then remember, from Ohm's law, we can write current as delta V equals to, delta V over R. And then delta V, we know is V start minus Vn over R. Okay, so we will always be using this to express all the current going in and current going out. Okay, so let's start. Oops. Okay. So KCL at the negative terminal of the op amp. So let us start. So the going in is this one. So where do we start from, right? We need to do V start minus Vn. We start from this node, correct? Let me circle it there. Yeah, in this red node, we start over here, and then we end over here. So what is the value of this node? The value of this node is given by the V battery, correct? Because down here is ground, which is 0. Then you cross V battery. This potential difference is V battery. That means up here must be V battery, correct? This is the negative terminal. This is the positive terminal. You climb up towards a higher potential. So up here is V battery. You just label it V bat. Okay. So for the time being, we're gonna do it like last time. Keep everything in algebra. Don't be tempted to sort all the values in straight away. Okay. Keep your working all in algebraic terms. So let me say again. Current going in equals to current going out. So the current going in is V start minus Vn. So we call this V minus. Yeah, V minus over the resistance. So it's Rs. Right? V start minus Vn divided by the resistance. equals to the current going out. So this one is the one going up, right? So where do we start and where do we stop? We start over here and we end, right? Our current travels through and then we end at this node. So this is our start. This is our stop, right? Start and end. So for current going in equals to current going out is V minus, right? Because it's a negative terminal, minus V out over Rf. Okay. So our job here is to just make V out the subject. Yeah. Let me check my working. Yeah, so it's a tedious process, but we're just gonna have to simplify it. Okay, so let us sub this one in, because we already discovered from our analysis that V1 is equal to V minus, right? So I can replace every V minus I see with V1, right? So this one becomes V1, this one becomes V1, right? I will just rewrite this whole thing. So V bat minus V1 over Rs equals to V1 minus V out over Rf. So yeah, our objective here is to make V out the subject, okay? Because why did I say that? Because they say no DC voltage appears at the output voltage. So this is V out. That's why we want to make V out our subject, because it's the term of interest right now. So now comes the algebra part. So just cross multiply, this time this time this. You will get RFV bat minus RFV1 RSV1 minus RSV out. Okay. So I'm gonna make this one come to one side because it has V out. So RSV out is equal to RSV1 plus RFV1 minus RFV bat. Okay? Because we want to make V out alone. Oh my god, my handwriting is trash. Okay. We want to make V out alone, so we move RS to that side. So what do? We divide each term by RS to remove this. So divide by RS, divide by RS, divide by RS, divide by RS. Okay, then we will get V out is equal to V1 plus RF over RS times V1 plus RF over RS times V bat. Okay, then what we can do is, you see, both of these have V1. Then we can factorize V1 out. So factorizing out, we get 1 plus RF over RS V1 plus RF over RS V bat. Okay. So what do we do here? Now what we should do is to sub in values. So now we can start to sub in values. So sub values, you should get V out is equal to 1 plus, so RF is equal to 10K, 10 kilo ohms. So I will put 10,000 like that, RS. Then V1 is given by the sinusoidal expression. Okay, refer to your question. Sine omega t minus 10,000 RS, don't have enough space, times 20. Okay. So the next step to do here is to expand it like this. So you take this entire term, what you do is expand to each term. So multiply to here, multiply to this, and this. So what will it become? It will become like this, quite ugly, but like this. 10,000 for RS times 10 plus 10 negative 3, 1 plus 10,000 over RS sine omega t minus So up here, if you multiply, it will become 200,000 over RS. Okay. So let's go back to what the question requires. The question requires that no DC voltage appear. What does DC voltage mean? First, let's take a look at AC. What does AC voltage mean? AC means for this sinusoidal source, like this, right? You see something waving up and down, up and down. How will AC appear? How will a DC appear? A DC, when you graph it out, voltage against time, it should just look like a constant value, right? DC means direct current, it's not changing, but AC is changing direction, so it goes back and forth, back and forth. So for DC, the value of the voltage is constant, correct? Let us go back to the terms that we have arrived down here. So again, this is just V out. Now, they say no DC voltage appears. So we had to scan through this entire expression and look for the terms that are constant values. Constant values. So what is a constant value? For example, this one is not constant. This term is not constant. Why? Because it has a sine term in it, right? If it has a sine term, then you know over time it will go up and down and up and down and up and down. So this thing changes with time. So therefore, this is not constant. This is not constant. But what about the rest of the terms? See? So this one, it is, right? It is a constant term. See, one is a constant. Everything inside here is constant. The resistance doesn't change with time. So all these numbers are just constant values. So we can say, yes, this one, this is our DC value. Then what about the last one? Here, agree with me that it is also a constant value, right? 200,000 is a constant. The resistance is also constant. It doesn't change with time. So therefore, this whole thing is a constant. So this is also constant. Now, you see, no DC voltage appears. So what should we do? Take the terms that we know that is a constant, this one and this one, then equate them to 0 because no DC voltage appeared. No means 0, right? So let us just collect those terms. So collect this term, and so 1 plus 10,000 over RS times 10 minus 200,000 over RS equals to 0. Okay, see the constant terms, which is the DC voltage, because they don't want any DC voltage, we just equate them to 0. Now we can solve for RS that satisfy this condition. So let us just do that. So when you expand this, you should get, okay, just multiply. So 10 plus 100,000 over RS, I expand, minus 200,000 RS equals 0. So this thing add together, 100,000 minus 200,000 will give me negative 100,000 over RS equals 0. Then bring this on to the other side. So 10 equals to 100,000 over RS. Then you make RS the subject. So move over here, and then this one move over here. So RS equals to, you divide it, you should get 10,000 ohms. In other words, 10 kilo ohms. Okay? Like that. So next question, what did they ask for? Next question, they asked, what is the value of V out using the RS that we solved already? So when RS equals to 10,000, what is the value of V out? So remember that this value of RS, what will it do? Okay, let me just copy down this very giant expression first, because we need it. So let me just copy and then paste it here. Okay, let me just clean it up, clean this. Okay, remember that value of RS will satisfy the condition that there will be no more DC voltage, right? So after you sub in the RS, what you expect is that all the constant terms will disappear because no DC voltage. So this will go away, and this will go away. You don't believe me? Let us just sub it in. So sub in this one, you get 10,000, right? Just now the RS that we solve is 10,000. This is 10,000, and this is 10,000, right? So this term is 10,000 divided by itself, so it becomes 1. This becomes 1, right? Then 1 plus 1 is 2. 2 times 10 is 20. So this is 20 plus 10 to the negative 3. Inside here is also 2, right? 1 plus 1. So this is times 2 sine omega t minus. See, you take 200,000 divided by 10,000. So 4 zeros, you can cut 4 zeros. So this becomes 20. You see, this is positive 20. This is negative 20. I told you the constant terms are cut out because that's the condition that we satisfied. So I just rearrange this. I get 2 times 10 to the negative 3 sine omega t. And this is our answer. Like that. Okay? So you see, no DC voltage appears when we sub in that value that we got earlier, which shows that we solved part A correctly. Okay? So I'm going to move on to question 9.2. Question 9.2 is another configuration, just a scarier configuration, but do not let that put you off or intimidate you. So let us just tackle this problem. Determine the output voltage again. So you tell me this time, what are the 3 holy steps whenever I see the little triangle that is the op amp? I want to see in the chat if you're paying attention. Anyone? Anyone? What are the 3 golden things you have to remember whenever you see op amp? Okay, V plus equals to V minus. Correct. Thank you, Sherman. Next step. I plus equals to I minus equals to 0. Good. Okay. Thank you, Samuel and Sherman. Then the last thing is what we need to do to start our working. Apply KCL. Very good. Okay, good. So, yes. Whenever you see op amp, straight away, V plus equals to V minus should register in your paper. Then I plus equals to I minus equals to 0. Then KCL wherever possible. Okay, wherever nodes possible. Wherever possible. Okay, so with that, let us look at the problem first. So see if it's simple. Okay, in this case, there's no voltage. I can immediately say, okay, this one is like surely 0, right? Because this one is not connected to ground. This one's also not connected to ground. So yeah, just acknowledge that over here, the currents are 0, so nothing going in there. Then we have to just straight away start with our KCL. Now, KCL wherever possible, right? Here, it makes sense to do KCL, right? I can analyze the currents going in, currents going in, out, whatever. Okay, you can also assume this is going out. You can also assume that this is going in. It doesn't matter as long as you are consistent. With that, I think we will just analyze the positive terminal first. So let me assume that it moves like that. Wait, let me see what my working did, because it'd be easier if I just follow my working. So for my working, I assume V2. Yeah, okay. I assume like this. So going in like this, going out like this, okay? Like I said, don't panic. However you assume the direction, it should give you the same answer. As a practice, I think you should try that out yourself. So you follow this way, and then you convince yourself by assuming another direction. You should get the same answer. So let us begin. So focus on the positive terminal node, and we start to do our KCL. So current going in equals to current going out. Let's see who's the current going in. This one, right? So we need to take V start minus Vn over the resistance. V start is here. What's the V start? It is this, Vs2. For short, I would just call it V2, okay? I don't want to write S unnecessarily. So I'll call this V2. So V start, which is V2, minus Vn, which is V plus. So V2, V start minus Vn over the resistance R2 equals to current going out. So current going out is this one. So V start minus Vn, the start is the positive terminal, the end is the ground. So V start minus V, this is ground, so it's 0, divided by R4, which is the resistance. Now, our objective here is just to make V plus the subject. Why do we want to make V plus the subject? We want to make V plus the subject so that we can equate it with V minus later, right? Using this fact that we acknowledged earlier. So let us go ahead and make V plus the subject. So cross multiply, this time this time this, we should get R4 V2 minus R4 V plus equal to R2 V plus. Collect all the V plus terms together. So R2 plus R4 V plus. Okay, I straight away factorize it out. Okay, R4 V2 still this side. Make V plus the subject, you should get R4 over R2 plus R4 V2. Okay, so this is your expression for V plus. So let us move on to do another KCL wherever possible. So another KCL would be at this node, right? At the negative terminal of the op amp. So let us assume a direction like this and like this. So KCL at that node means current going in equal to current going out. So the current going in is V start minus Vn. In this case, V start is V1, right? This Vs1 should give me V1. And current going out is, V start is V1. Ooh, I have no idea why my OneNote just crashed. Something's wrong with my OneNote. Wait, something is wrong with my OneNote. I apologize. Okay. I'll just settle with that later. So where was I? Okay, we were doing KCL at the negative terminal, right? So, oh no, why did it destroy all my working? Yeah. Okay, so this is V1, right? This is V start, and then this is Vn. Vn is over here. It's V minus, correct? So KCL at negative, right? It's negative. Means V start minus Vn divided by R1 equals to, let us check the current going out. So current going out, it starts from here and then ends at here. This voltage is V out, right? Because they indicated here V out. So V start is V minus. Oh, let me just do this. V minus V out over R3. So we want to make V minus the subject so that later we can equate to V plus. So this time this time this, we will get R3 V1 minus R3 V minus equals to R1 V minus R1 V out. Then just collect the terms with V minus, we get, okay, put this to the other side, we get R1 plus R3 V minus, then move this to the other side, we get R3 V1 plus R1 V out. Then we make V minus the subject, so V minus equals to R3 V1 plus R1 V out over R1 plus R3. Okay? Yeah. Let me just neaten this. So it's like that. Okay. So now we can go ahead and make use of the fact, make use of this fact, the first one, to equate the term, the expression that we derived. This one with this one. Okay? So let us go ahead and do that. So let me just start by saying V plus equal to V minus. Okay, let me just check my working if I'm correct. Okay, yeah. So with that, we can say R4 over R2 plus R4 V2 is equals to R3 V1 plus R1 V out over R1 plus R3. Okay, so next step I did was what should I do? Sorry, I'm seeing if there's any way to make this simpler. Okay, I have no choices. Okay, so we want to make V out the subject. Yeah, we want to make V out the subject, right? Because, yeah, determine the output voltage. So what we do is, let me just split this to half. Okay, when I split this fraction to half, I'll get this one, V1, over R1 plus R3 plus the other side over the same denominator. Okay, just copy this down, R4 V2 over R2 plus R4. What we do is we move this one to this side. We should get R2 V2 R2 plus R4 minus R3 V1 over R1 plus R3 equals to R1 V out over R1 plus R3. Okay, to simplify stuff, because we want to make this on the subject, right? So what we should do is multiply all this whole equation by R1 plus R3, right? We want to remove this denominator. So we get R2 V2 R1 plus R3 R2 plus R4 minus. So when you multiply this with this, they cancel, right? The denominator, this will cancel with this. So we simply get like that equals to like that, just the top, because this one also cancels with this one. So we get that. Okay, so now we want to make V out alone, so just divide everything by R1. You should get, so let me just skip to the end, you should get V out is equals to R4 R1 plus R3 over R2 plus R4 R1, and the V2, I'm just gonna put it to the side over here, okay? So V2 minus R3 over R1 V1. Okay, I'm doing this very delicately. It's quite slow and tedious, right? But I'm trying to be careful because if you make a mistake, it's a very painful process. Yeah, so forgive my slowness for the time being. Now we can begin to substitute in the resistances. So if you sub in the resistance, you should get 11, 1 plus 13 over 3 plus 11 times 1. Then V2 minus 13 divided by 1, V1. You punch this into your calculator, you should get V out is 11 V2 minus 13 V1. Okay, what do you do next? You sub in the V2. So I know you could have one shot V2 and V1 also substitute in it, but I just want to make it clean first. So what did they say V2 is? Go back up. They told me V2 is this. And then V1 is this. So sub in V2 and V1, you should get so 11 times 3.1 times 10 to the power of -3 cosine omega t minus 13 2.9 times 10 to the -3 cosine omega omega t, like that. So you take this times this, this times this, and then because both of them are cosine omega t, you can just add up their coefficients, right? When you calculate this, you take this minus this, then after that, at the end of the day, you should get negative 3.6 times 10 to the power of negative 3 cosine omega t. Yeah. So that's your answer. I know it's quite off-putting with all this algebra, but you will come to realize that it is not too bad. Just try to do it yourself. Try to do it on your own. I know you've seen it already, but try to like pause it and like, okay, it's a bit tedious when the first time you do it. I mean, the first time you watch me do it, but convince yourself that you can indeed do it. It is possible by just doing it yourself. Okay, it's not difficult. It's just tedious, right? Because at the end of the day, the only circuit knowledge that you really need to know for op-amp is this 3 statements that I've told you already. The rest of it is really just mathematical only, correct? Okay, so convince yourself that you can do it and all should be good. Okay, so I need to take a drink. I'm so damn thirsty. Okay, so let us continue. I think that's all, right? They only asked us for the output voltage. Yes. Okay, so I'm gonna go to question 9.3. Okay, so again, I have certified Samuel and Sherman to be able to tell me the first 3 steps. So again, we see our little triangle, the op-amp. So now we know that we should immediately write V plus is equal to V minus, then I plus is equal to I minus is equal to 0, then KCL wherever possible. Again, you don't need to write KCL wherever possible. I'm just telling you that this is a step to take. But it's a good habit to remind yourself as a beginner. Okay, so they told us that this shows a band pass filter configuration, right? Like I told you, op-amp can be used for 2 things. Number 1, amplification, right? The name already says it, operational amplifier. Number 2 is a filter. So yes, surprise, surprise, amplifiers can be used as filters. Yeah, so let us not talk too much. We can start to do the analysis. So just have a look at the op-amp. Can we simplify anything? Yes. So they told us that, you see, focus on this positive terminal. It is connected to the ground. The ground is 0 volts. That means we know for a fact that V plus will be equal to 0, right? So from that statement, we can say V plus equals to 0. But look, we've already established that V plus must be equal to V minus, okay? That's just the property of ideal op-amps. It must be that V plus is equal to V minus. By that logic, that means that this one, V minus, the negative terminal, must also be 0 volts. Okay, this must also be 0 volts. So now we need to take KCL wherever possible, correct? So we know that there's no current entering here, there's no current also entering here. So, but we can assume that there's current entering here, correct? And current leaving out through here. So let me see the direction that I've assumed so that I have a reference. Yeah. So I've assumed it this way. So going in at this, coming out at this. Now, let us check because this configuration is quite messy, correct? So the current going in is going through this resistor and this capacitor combined. So that tells me that if I want to do the delta V over R, in this case, I cannot use just R, correct? Because there's a capacitor, I need to use impedance, Z, okay? Impedance. So I must use the combined impedance of these 2 devices for the current going in. Now, let us discuss about the current going out. The current going out, where does it go through? You see, as it goes up here, it will split it will split into here and into here. Then it will go through the resistor and go through the capacitor. So that means current going out will go through both the R2, the resistor here, and C2, the capacitor here. So what we should do is think of these two as a combined device. So what we need to do is combine their impedance together when we do the current going out. So we can redraw this problem like this. We can redraw this problem like this. So what I want to do is combine these two impedance as a device called ZA. Combine these two devices, combine these two impedance as a device called ZB. So you simplify the problem, it will look like this. So this is my op amp. This is my negative terminal, positive terminal, going to the ground. This is my V1. Sorry, V in. So this is the ZA that I was talking about. Then it will go through here, and this is the ZB that I was talking about. Then it will come out like that, like that. So what I was doing is I was basically copying the whole thing, except I replaced the combined devices like this as a single device like this, just to simplify my problem. And then this one will match these two combined devices, this and this. Okay? So yeah, let us just do the KCL at the negative terminal. So current going in, current going out. The one going in, it will be V in minus V minus over ZA. And then V minus, yeah, V minus, start from here, we end at here, right? Current going like that. So V start minus V end divided by ZB. Okay? Then we already established that, see, V minus is equal to 0 because the positive one is attached to the ground. Then the positive terminal will be equal to the negative terminal. So this will be 0. 0 here, 0 here. Okay? Then, so what we need to do is we rearrange to get the transfer function, which is the frequency response. Remember? Frequency response is given by, can anyone tell me? I want someone to tell me. What's the frequency response? We discussed this last week already. The formula for frequency response is... Wait, tell me. Someone. Sherman. Hold on. Enjie. Ain. Who? What's the formula for H? H is given by V out over V in. Okay, thank you. I don't know why it took it so long. Yes, V out over V in. So our objective is to get the V out over V in. Okay? So let me just simplify this. So ZA is equal to negative V out over ZB. Right? See? There's already V out at the top. What we need to do is make this one go down here. Correct? So when we do that, we will, at the end of the day, you will get V out over V in is equal to minus ZA over ZB. No, sorry, Zeb. ZB over ZA. Okay, be careful. See, I just almost made a mistake there, right? Because you move this one down, then you carry this one up, and then you move the negative sign to that side. Okay, so you get negative ZB over ZA. Okay, so now we need to find ZB and ZA, correct? So let us just do that. Let us tackle with ZB first because it is more difficult. So ZB, look at the devices. These two are in, the R2 and C2, they are in parallel. So we need to use the parallel formula, total impedance in parallel. So that means 1 over ZB is equal to 1 over R2 plus 1 over J omega C2, correct? So if we make ZB the subject, we should get 1 over R2 plus J omega C2, right? But you see, just to clean things up, you see this fraction inside a fraction. So what I will do is try to get rid of this fraction. How to do that? I want to get rid of this denominator, correct? So multiply top and bottom by R2 times R2 times R2, this whole thing. So this times this, it will cancel, right? R2 will cancel with R2. Then I will get R2 at the top over 1 plus j omega c2 R2, right? This times this also. Okay, that's just to simplify the problem. Next we want to find ZA. ZA is easy, correct? Because the resistor and the capacitor are in series. So what we do to find the combined impedance is just add them together. So that means ZA is given by R1 plus 1 over j omega C1, like that. So now that we have these two, we can finally find the frequency response, right? We have the ZB, we have the ZA, we can sub it in. So the frequency response is given by negative ZB over ZA. Our ZB is given by the one at the top, which is R2 over 1 plus j omega C2 R2 over this one, which is R1 plus 1 over j omega C1. Okay? So, see, we have a fraction divided by something, right? So what will happen? You just take this times this, right? I hope you all know that, right? When we have a fraction like this, a over b divided by c, this will just become a over bc, right? I hope everybody knows that. Because it's like saying this is like saying a over b times 1 over c, which is a over bc. Okay? So I just want to clear that algebra up because I don't want people to get confused. So what you get is negative R2 over, in the denominator, we get 1 over j omega C2 R2, and R1 plus 1 over j omega C1. So our job here is to just expand and simplify the bottom. Yeah, I know. Terrible, right? So this times this, what will you get? It's just so R1 plus 1 over j omega C1 plus j omega C2 R1 R2 plus C2 R2 over C1. Okay, so how did I get that? So this times this times this, that's how I get R1 plus j omega 1 over j omega C1. Then take a look at this times this, I get this and this. Okay, so just expand and simplify. Our job here is to look at the denominator, group them into the real component and the imaginary component. So who are the real components? The real components are those without j, right? You see, j is over here, j is over here. So that means these two are the imaginary component. Okay, I will group them to one side, and then I will group the real numbers to the other side. So who are the real ones? Those without the j. So R1 doesn't have j. This guy also doesn't have j. So I will group them to the left-hand side. So this negative R2 over R1 plus C2 R2 over C1 plus. Okay. Okay, I'm not gonna do any shortcuts. So remember what I said? Whenever you see 1 over j, you can turn it to negative j, right? 1 over j means negative j. So this one, I'll bring it to the front. So I'll copy this down. So it's j omega C2 R1 R2. And then this one can turn into negative j. So it becomes negative 1 over 1 over omega C1 j, right? I'm going to say that again. So I notice the 1 over j, I will turn it to negative j, like that. Okay. Now I can clearly see who are my real terms. So these are the real numbers and these are the imaginary one. So for simplicity, I will factorize out the j. Okay, factorize out the j from this right side. So what you get is, yeah, I know when you're doing your own work, yeah, you can skip a few steps. I'm just making it clear so that everybody can follow, because I know the algebra is disgusting in this problem. So yes, you may skip a few steps to just hurry up the process. Okay, so what do we do? We just take the limit, okay? Because this is our h, right? This is the expression for our h. So we want to identify what filter it is. Actually, they already told us it is a bandpass filter, but let us convince ourselves that it is. So to find the low frequency limit, you take the limit of h as omega approach 0, right? Going to lower and lower limits. So let us just copy this. Okay, you copy this, paste. So as omega approaches 0, where is our omega? Our omega is here, our omega is here. As omega approach 0, this thing goes to 0, right? 0 times something is equal to 0. Then as this goes to 0, all of this, see, 1 divided by 0 is infinity. So this whole thing will go to infinity, right? So you see this one already disappear because it's 0. Then you see something plus infinity should be infinity, correct? Something plus infinity should be infinity. So the whole denominator is actually infinity, right? This whole denominator will go to infinity. Then you see something divided by infinity will be 0, right? A constant divided by some huge number will become a very small number, which is 0. Okay, so let us take the high frequency limit. So paste this again. So when this goes to infinity, see 1 divided by infinity is 0. So this goes to 0. Next, omega here goes to infinity. Now take a look at the whole bottom. Something plus infinity should all go to infinity, right? This whole bottom, let me just use a different color. This whole bottom will go to infinity. And see, something divided by infinity will be 0. A number divided by a really big number is equal to a really small number. So take a look at this. Normally, we would have 0 and a non-zero number, right? But now, see, when I go to the low frequencies, I get 0. When I go to the high frequencies, I also get 0. So this shows that it must be a band pass filter, right? Band pass filter means there is a band of frequencies that has some gain. Okay, let me show you what I mean. So when I show you the gain versus frequency graph, see there will be just a band of frequencies that allow the current to pass through. Right, there will be some gain here, while the rest is just 0. The rest is just 0. So see, since it's a little band of it, it looks like a band, right? A band is a little rectangle. So we call this a band pass filter. See, low frequencies, 0 gain. High frequency, 0 gain, which is what we get. See, low frequency, 0 gain, high frequency, 0 gain. So we know that this is a band pass filter. Okay, so we are convinced that this is a band pass filter. Now, what did the question ask for us? Determine the band pass gain. See, in the low and high pass filter, the non-zero limit will give us the maximum gain, correct? But how do we get it in the band pass filter? See, if we take how do we find this exactly, the value of this height, this one, right? That's what the question is trying to ask. What is the band pass gain, which is the maximum gain? We don't know. Normally, when we did the low pass filter and the high pass filter, the non-zero limit will give us the answer, correct? But how? See, if I take the low frequency limit, it's 0. The high frequency limit is also 0. How do we get the in between? So this is a fact that you just have to know, have to remember. Why is it the case? I'm also not clear, but just know for a fact. Just know this for a fact. Okay, so heed my words and take this again to your grave. For bandpass filters, max gain, which we said is H naught, occurs at resonant frequency. Okay, resonant frequency. Where imaginary part of the H that we got, the H function that we got just now, is equal to 0. Okay, the imaginary part of this is equal to 0. The imaginary part of this. Imaginary part. I shouldn't put equal to 0. Hold on. I'm just going to say is 0. Okay? What does that mean? So let us have a look at our H function that we got just now, which is this one, right? Where is the imaginary part? This one, right? Because it's in front of J. In front of J is the imaginary part. So to achieve the maximum gain, to achieve this maximum gain, this will occur at, the maximum gain will occur at the resonant frequency. Let's call it omega R. Okay, omega R is resonant frequency. And what will happen at omega R? This will all become 0. Remember, this is our expression for H, right? So when this is equal to 0, then the rest of it gives our maximum gain. Okay, the rest of this, you literally just equate the imaginary part to 0. That's why I was so hardworking to separate out the real part and the imaginary part, so that here, when they ask for the maximum gain, I just take the imaginary part, equate it to 0. The rest I copy down. This is my maximum gain. Okay, so H naught is equal to the rest of this. I just copy it down. So R2 over R1 plus C2 R2 over C1. Okay, so I'm going to emphasize again, this is an important fact, okay, for finding the max gain of bandpass filters. Yeah. You just sub all the values in, so I'm not gonna do it. I'm not gonna manually sub it in for you. So you sub in R2, R1, C2, R2, C1. After you sub in, you plug in the numbers. In fact, you should take the modulus of this, right? Because there's a negative here. It doesn't make sense to get a negative gain. So just take the modulus of this. So what you get at the end of the day is 44.53. And if you want to change this to decibels, then sure, you go ahead and do 20 log 10 of this 44.53. You should get 32.97 dB. Okay, decibels. Okay, I want to add an additional question because it is possible that they ask you this. Okay, the additional question is this. Additional question. Find the resonant frequency omega R. Okay, find the resonant frequency. Yeah, it is possible that they ask you how to find the resonant frequency. So what is the condition for resonant frequency again? I said, like I said from the top here, resonant frequency occurs when the imaginary part of this function is equal to 0. So what do we do? Take a look at our H function. See, this part that I highlighted, this part is equal to 0. So let us just clean this up first. So take the green highlighted part and then equate it to 0. So omega omega C2 R1 R2 minus 1 over omega C1 is equal to 0. This is the imaginary part. I just equate it to 0 to find the resonant frequency. So because they labeled resonant frequency as omega R, right? So let us just follow suit. So this is omega R, this is omega R. Now, just make omega r the subject. So let us get rid of this denominator by multiplying omega r C1 on both sides. Right? So when you do that, this times omega r is just omega r squared. Omega r squared. Then C1, C2, R1, R2. Then this times this, it will cancel itself, right? This cancels with itself. Okay, so this becomes -1 equals to 0 times something is equal to 0. Then move 1 to the other side. Then you make omega r the subject. So omega r will become 1 over square root of C1, C2, R1, R2. Yeah, so if you're interested, you can sub in the values. But this is how you achieve the resonant frequency. Take the imaginary part of the function, of the h function, the transfer function, then you equate it to 0, solve for omega, that will give you your resonant frequency. Okay, if you're interested, just sub in the values, but this is enough. Okay, and that's how you achieve your resonant frequency. Let me see if there's any other questions. Yeah, they just asked for that, and I gave you all an additional question. It is important to know, so that's why I decided to bring it up here. I think we're end for the day. Yeah, so let me just stop the recording. Oh, okay. Let me see what Samuel said. Can I see the additional question again? Okay, sure. Oops, I forgot. I don't know why I turned off this screen share. Good tips once again. Thank you, Sherman. So, yeah, I mean, yeah, I don't have to flash this to you again because you can always see the recording. But yeah, please take note of the things that I emphasize to you. Okay. So, for example, op amp. Sorry, Samuel. I'm gonna wait first for that question, for the additional question. So for op amp, please put this as a tattoo on your body, or just bring it to your grave. Okay, these three things. So whenever you see the op amp, immediately what you write down on your paper is V plus equal to V minus, I plus equal to I minus equals 0, and then KCL wherever possible. Okay, so wherever possible is really, it comes down to practice. I mean, it wouldn't make sense to do a KCL, for example, somewhere here, right? What's the current going in? What's the current going out? It makes no sense to do that. But something more complicated over here, then KCL is possible, correct? So that's what I mean by KCL wherever nodes possible. Okay, yeah. Remember these three statements. It's the most important to get started with op amp. Yeah, you need to remember your impedance formulas from last week. What else? Oh yeah, taking the limits. Okay, and this one also. So for bandpass filter, it's I don't know why it's an undiscussed fact that to find the bandpass filter, to find the resonant frequency, sorry, the maximum gain occurs at resonant frequency. So let me draw for you what a real bandpass filter graph looks like. See, this one is ideal, right? If it's ideal, then it's a very sharp and nice rectangle. The unideal one will look like something like this. So it look like this, like this, like this. See, it tries to look like the rectangle, right? It tries to look like the rectangle, but it cannot. So the maximum gain is at the very tippy top right here, which is H naught. This occurs at your omega r, right? The resonant frequency. And how to get that? So this is the fact that you have to recognize bandpass filters maximum gain occurs at the omega r. At this omega r, so the transfer function that you have derived, look at the imaginary part, equate that to 0. So this is equal to 0. So that means the rest of it will be your maximum gain. Okay, so you just copy down the rest of it. Then to find that omega r, we know that if the imaginary part is equal to 0, so you equate this to 0, you solve for omega, tada, that is your resonant frequency. And this is something I want to emphasize, but the recording is over. Damn it. Okay. what I emphasize is you shouldn't memorize all those nonsense like you know, in the lecture video you see this RF over RS V out, something like that, blah blah blah, whatever. Oh sorry, I think it's V out VS. So should you memorize it? The very decisive answer is no. Okay, why? Because this formula, right, depends on the configuration of the circuit. If the circuit is more complicated, which it usually is, then it's game over. They'll never replicate that same configuration used to derive this formula. Okay, never. They never will. They'll always give something different. So memorizing this formula is useless. What are you supposed to do? Memorize this thing instead. You know, V plus equal to V minus, I plus equals to I minus equal to 0, and KCL wherever possible. Okay, this is the thing that you should remember, not this. Okay, so don't be tricked. Yeah, I was also tricked when I was a student also to learn this. Okay, you're not supposed to learn this. You're supposed to learn this and derive everything from scratch. Where does the derivation process start? Dude, when you did the KCL. Because if you want to convince yourself, go to the lecture notes and you do these three things. Okay, you know, write down these three statements and then you begin to derive it on your own. You will eventually get this. So this is a result. Okay, this is a special result, in fact. Special result. And you know, special results needs special conditions. What is the condition? The configuration of the circuit. So please don't memorize this formula that they give you. Remember the technique to get it yourself. Okay, you need to derive it always from scratch. Okay, always. Yeah. So as a trickle. Okay. Okay, so I want to show Samuel the extra question. Yeah. So this is the additional question. Find the resonant frequency. Yeah, it's possible that they ask you. They've asked this before many times in the finals. They've asked it in my finals. So I know I said this like 3,000 times already. Yeah. So just to refresh Samuel's brain, this thing over here is the imaginary part of your H function. Okay. We know that at resonant frequency, the imaginary part will be equal to 0. So you just equate it, you solve for omega, tada, that is your resonant frequency. Okay. Yeah. Yeah, okay. I never memorized the resonant frequency formula. Like I know they put it blank out like omega equals to RF over RS or something like that, or CS or something like that. Yeah. I don't really bother with this. I just will derive it all the way from scratch. It's in fact the required thing to do. Okay, it's the required approach. Yeah. So there's no golden formula for you to remember in this chapter, I guess. Only thing for you to do is just derive it all from scratch. Yo, Samuel, keep it PG. Okay. If that's it, you can all leave already. Yeah, there's nothing much to discuss about. The practical function of what an op-amp what an op-amp does. I saw that in tutorial 11 it covers it, so I'm not gonna cover it here. Otherwise, because you will forget eventually by the time you reach there. Okay, so I will talk about that when we cross that bridge. So good night, everyone. You all can leave already. I'm not gonna hold you back because I have things to do myself. Yeah, yeah. Thank you, Samuel. Thank you for joining. Yeah, thank you, Sherman. Thank you for joining me tonight. Yeah, see you next week.